Welcome to the course Java Development. We're going to talk about thread stack and heap space and synchronization. Make sure that you are subscribed inside of our YouTube channel right here and follow our Instagram page. We're bringing this to you, and let's move on. Well, welcome to the class, guys. We're going to build a counter project that's going to give us an overview of the thread variables problems, and we're going to use synchronization to solve. We're opening our integrated development environment. Okay, the first thing that we're going to do is to create a class that's going to be the boilerplate of our counter that is going to count from 25 to 1. Create a class to represent the thread where we're going to run our counter. Use two threads to run the same instance of our counter. Let's create a class here and give it a name of counter. Inside of this counter, we're going to have a variable I, and we're going to count from what? Oh, let's create a method that's going to be void, and the name is going to be count now. That's going to be responsible for counting from 25 to 1, as we saw, while I is greater than 0 and I minus. Let's just print the thread name here, concatenate with I equal to plus the value of our counter. The second part is to create a class that's going to represent the thread where we're going to run our counter. So let's create counter thread. Here we're going to extend, and here let's just hold one instance of our counter. This is going to be our counter, and create a constructor right here so that we assign a counter when we instantiate this thread. So that counter is going to be the counter that comes from the constructor, and let's override the method run. Override the method run. What's the extends thread. Okay, override the method run, and here what we're going to do, simply run that method responsible for doing the counting for us. So counter.count now. Now it's time for us to create two instances and start to run this counter. Okay, let's create one instance here of our counter. Counter is going to be new counter. Create an instance of this thread. Counter thread 1 is going to be new counter thread, and we're going to pass this instance right here. Okay, Control D, counter thread now is 2. We pass the same instance, but right before here, let's assign a name to this counter thread 1. Set the name to thread 1, and for this one, let's set a name counter thread 2. Set name to be thread 2, and we are pretty much done. Let's just start these two threads. Counter 1 start, and the 2 start. Okay, let's run it. Great. Okay, here we have our outputs. Let's just open this class. Thread 2 is showing 25, thread 1 25. Okay, thread 2 24, thread 1 24. You may not have the same output as I have. Don't worry, threads don't execute in the same order in all the machines. We are just scheduling the threads, and the CPU is going to know when it's going to execute. So don't worry if you don't have the same order as I have. Here the threads are just changing each one. First the thread 2 shows us this output, then thread 1 shows the output, thread 2 does the same, and so on. The reason is because this thread was executing, it got suspended to give the opportunity to the thread 1 execute, then it was suspended, thread 2 did its operations, thread 1 also did, so it's just switching between suspension and execution. But we have the outputs in the correct order for thread 2, because we see that it goes 25, 24, 23, 22, 21 until 1. The same does happen for the thread 2. Thread 2 and thread 1 have the values from 25 to 1. But let's make something different right now. Just write I. We're referring to this one, I, not the local one. Surprise. Yes, surprise. But I don't want this output, I want a different one, so help me explaining to you and you can understand it easily. This one is better. Yes, you can see the thread 1 has 25, thread 2 25, thread 2 24, and then thread 1 23, but you didn't see 24 for thread 1. What happened? Well, these values are now being shared among these two threads. The first time it was about local variables. Local variables are stored on the thread stack, therefore each thread has a copy of the variable and has its own value assigned to that variable. Now this is here different. This is about a heap. First, when we wrote int I equal to 25, that was a variable stored inside of the stack, and the thread 1 could not access thread 2's stack. The same, thread 2 could not access thread 1 stack, so those variables were local and assigned to each thread individually. So that's why the thread could execute and find the value of 25 or the previous value, do modifications, and only see the value for itself. It's all to work with local threads. When our computer reserves a space for the variable, it uses the stack at that time. And now the thing is different because I is stored inside of the heap, and heap can be accessed by both of the threads. Remember what I told you. That's why we have these values being shared. When thread 1 does a modification, the thread 2 can see that modification. First, we have thread 2 showing us 25, correct? Then thread 1 showing us again 25. Why? Because you probably may think that it had decremented. What happens the first time the thread executes and sees 25? Okay, 25 is greater than 0, right? So let's build the string here and output. Okay, thread 2 outputs. Let's go back here and decrement. But before this thread 2 went back there, it got suspended. After it got suspended, what happened? Thread 1 had the chance to execute. That value was still 25 of I. I was greater than 0, yes. So it built the string thread 1 and it printed right here. Okay, we have here now thread 2 showing us 24. What means that thread 1 after printing the value got suspended and thread 2 continued with execution. Thread 2 was stopped here when it was blocked, so it came here, it decremented the value to 24. 24 is greater than 0, yes. Thread 2 built the string and printed here. Fine. And now the value of this I is here. Then thread 2 came up here and didn't do anything. Thread 1 came here and continued with the execution because it was suspended right here. It came up here, decremented the value. The value right now is 24 because the thread 2 had modified, decremented from 24 to 23. Built the string, showed the result, and now thread 2 has the opportunity to execute. The value is 23. 23 minus 1 is 22, and it is showing. So that's what's happening. At this point, you can see that the thread 2 had the possibility to execute many times. You may think that this is an error 11. Okay, we have this one, thread 2. What could have happened is that the thread 2 executed this line when I was 12. It built the string and output it to the console. Then thread 1 had the opportunity to execute. It decremented the value from 12 to 11. It built this string wall here, but it didn't have the opportunity to show to the console. It can be suspended anytime. Maybe it was at the time when it was calling the system part or the out or the print line. You don't know when it was suspended. And when it was suspended, it had decremented the value from 12 to 11. It gave the chance to the thread 2 to execute. The thread 2 saw that the last variable was 11. It decremented to 10. It had the opportunity to run many times from 10 to 1. After this thread terminated, thread 1 had the opportunity to execute, and what it did, it printed the information that had been built. After that, thread 1 came up here and saw that, hey, the last value is 1 and I'm decrementing 1 unit, so it's 0. 0 is greater than 0. No, stop it. You can see the problems that can arise when we deal with that shared resource. This is one of the problems of shared resource inside of the threads. To solve this, with local variables, we know that each instance is going to hold that value on inside of the stack. There is no problem, but we may want to work with this way. All we have to do is to synchronize. Synchronization is the key point to solve this interference or this race condition, mostly known. Synchronization is just a tool to control the access of multiple threads to a shared resource. We're going to synchronize to prevent the thread interference and guarantee the integrity of our variable. We have here a keyword in Java used to make the synchronization work, which is synchronized. Here we have, if we run it again, we have to expect good result. You see, everything is working fine. What happens is that when the method is synchronized by a thread and other thread tries to execute the synchronized method, the access to execute will not be granted until the thread which is currently executing that particular method, which is synchronized, terminates the execution of all that method. So this method needs to execute, then the access is going to be granted to the next thread trying to execute the same method. So all parts synchronized are protected against the interference. Not all the program, but only those parts that are synchronized. So if we had other parts that could be vulnerable to interference, we could still have the interference. We can make the synchronization of methods and blocks. So it's our job as developers to synchronize methods and make sure that our program is working very well. End of the class. Counter project done. Problems with thread synchronization done. Follow us in our Instagram. We need to grow, please. Subscribe to our YouTube channel. Share this video with other developers and your friends because they need to work with threads and they need to know how to do that.